Here we shall show that studying in molecular dynamics simulations velocity-velocity autocorrelation function allows one to determine vibrational frequencies in the given system as well. This is a rather long proof, so I will give just main ideas, and there will be a problem for you to go through, in which you will be able to do this calculation in detail. So first of all, what we shall do, we shall demonstrate that the Hamiltonian of the whole system can be split in the sum of Hamiltonians, each associated with normal modes. So we shall consider um, um, a harmonic Hamiltonian. Here you have the kinetic energy and the potential energy, only the harmonic terms. Correspondingly, the Lagrangian would be given as a difference of the kinetic energy and the potential energy. In the Lagrangian, we use velocities. In the Hamiltonian, we use momenta. Because in the Lagrangian, velocities are conjugate to the displacements. In the Hamiltonian, momenta are conjugate to the displacements. So indices I, j, they correspond to degrees of freedom of a given system. We learned before that potential energies of our harmonic system, here this energy is written in a matrix form. Phi is a force constant matrix, and U is the vector of all displacements U, I. This can be written y normal coordinates. And normal coordinates y lambda, and index lambda is used to number these normal coordinates, each associated with the frequency omega lambda. These normal coordinates are given by this expression. These are some specific linear combinations of the displacements ui with the coefficients which is related to the mass of atoms and the eigenvector of the dynamical matrix y lambda. So in the matrix form, that y lambda, which is a scalar, is written like this, where this, as I said, capital Y lambda is an eigenvector of the dynamical matrix. So M is a matrix of atomic masses, a diagonal matrix of atomic masses, and M in the power 1/2 is a diagonal matrix in which along the diagonal you have square roots of atomic masses. From this expression, we can easily work out the y lambda dot, the time derivative of this normal coordinate, and it will be related to the velocities of atoms. Then we can solve this equation with respect to these velocities. For that, we need to multiply both sides of this equation by y lambda j, this is eigenvector again, and sum over all lambda. So in the left hand side, we will then have this. In the right hand side, we will have that, in which we can recognize in this sum the completeness condition for the eigenvectors. So this will be equal to the Kronecker symbol ij. And therefore, we can, from here, work out the velocities of our degrees of freedom j via the sum over all normal modes. So this is simply a solution of that equation with respect to these velocities. And we will be using this kind of trick several times when we write equation in which normal modes are expressed via atomic displacements or via velocities. And we would like to write the inverse relationship in which velocities, for example, or atomic displacements are expressed via normal modes or their velocities. So we take these velocities and substitute in the kinetic energy. And here's this transformation we need to do for the kinetic energy. So this is my kinetic energy. I replaced twice these velocities in here. So I have a double sum over lambda because we have a single sum here. And now this is the orthogonality of two eigenvectors, lambda and lambda prime, which is again a Kronecker symbol. And so you see the kinetic energy becomes a sum over all normal modes contributions. So that means that Lagrangian of our system, we won't be using Lagrangian, but I'll just mention that. The Lagrangian of our system is composed of two contributions. Kinetic energy is the sum of all contributions coming from all the normal modes, and the potential energy is also a sum of all contributions coming each from the normal mode. So the Lagrangian is actually a sum of Lagrangians, each associated with a particular normal mode. So it's completely additive in the normal mode representation. The same can be done for the Hamiltonian as well. In the case of the Hamiltonian, we need to work out what is the momentum p lambda conjugate to the normal mode y lambda. For that, one has to differentiate the Lagrangian with respect to the velocity of that normal mode. And so we need to differentiate this, and we obtain just y lambda dot, which is something you would probably expect, because in the kinetic energy, there is no mass here, so mass is equal to 1. Therefore, the momentum would be mass times velocity, so mass is equal to 1, so we will have just that. All right, so an expression for the velocity of the normal coordinates we had before. So therefore, we have an expression which relates the momentum p lambda with the velocity u dot. And of course, one can replace this velocity with the momentum p if you divide by the mass, and you will get this expression which relates the new momentum p lambda and the old momentum pi here. And again, by using a similar trick we used here, we can actually relate back pi via p lambdas if we need to. And we will have to use this later on, I suppose. So we have just discovered that kinetic energy is the sum of the squares of the velocities, but velocities are the momenta, so it can also be written as the sum of the momenta, and therefore the Hamiltonian of our harmonic system is given by this. So you can recognize in the expression in the brackets a Hamiltonian of a single harmonic oscillator with frequency omega lambda and unit mass. So the total Hamiltonian of our system in the harmonic approximation is the sum of Hamiltonians for each normal mode. And therefore, we can write equations of motion for the whole system by simply combining equations of motions for each normal mode. And these equations are simply these harmonic oscillator equations, or if you turn them into the y lambda, recalling that p lambda is y lambda dot, you will have this harmonic oscillator equation with a solution containing a constant a lambda and a lambda star, because here is a complex conjugate part which is necessary to ensure that y lambda is real. So we know that the total Hamiltonian of our system can be written as a sum of Hamiltonians for each normal mode, and normal modes and the corresponding to them conjugate momenta are expressed via displacements and momenta in the old representation. We can solve these two equations with respect to ui and pi with the same trick as I explained before. And for ui, for instance, ui dot, actually, we got something like that, but very similar expression is obtained for ui. All right, and these are written here. So this is ui via y lambda, and this is pi via p lambda. And now we know what y lambda is, and p lambda is just time derivative of y lambda. So we can substitute them in here, and we arrive at this formula here for these two displacement and the momentum. What is yet undetermined are these constants, a lambda and a lambda star. So we need to determine them, and this can be done in classical mechanics by applying initial conditions. So we have to assume that we know initial displacements and initial momenta, and Therefore, taking time equal to 0 in these equations, we obtain these two equations where in the left hand side we have initial displacement and the momentum. In the right hand side we have this linear combination of the a lambda arbitrary constants. Solving these two equations, one obtains this. So in order to solve them, again, you have to solve this equation with respect to this a lambda. This is achieved by multiplying both sides of this equation by y lambda prime I and summing over I both sides. So once we know the constant a lambda, we substitute them in here, and finally we can write down the time the evolution of the atomic displacements and their momenta for the harmonic system. So these equations are exact. They contain these eigenvectors of the dynamical matrix, the frequencies, and the initial displacements and the initial momenta. So up to this point, what we have just done, we simply presented a general solution of the harmonic problem for the Hamiltonian, which is written in the harmonic approximation. So we have many atoms which oscillate within the harmonic approximation, and their displacements and momenta change in time according to this formula we have just obtained. Of course, the question arises where we can take this initial displacement and momenta from. So the only thing we can say that the system at initial time must have been at thermodynamic equilibrium, and therefore it should follow the canonical distribution for the given temperature T. So what we then should calculate is the averages of this statistical averages of a product of the displacements, momenta, and displacements and momenta, and see what happens. Eventually, we would like to calculate this kind of autocorrelation function for the momentum. So let's see how we shall do this. First of all, when we write all these statistical averages, we can use our original coordinates and momenta. So our displacements and momenta, this would come in the statistical integrals. But we would rather like to use normal coordinates and correspondingly conjugated momenta, because in those variables the Hamiltonian becomes additive. So our Hamiltonian is constructed as a sum of the Hamiltonians small h lambda associated with each normal mode. To go from these old variables to these new variables in the phase space integral, we have to calculate the Jacobian J, and the Jacobian is given in a usual way as a determinant associated with the derivatives of the old variables with respect to the new ones. And because the displacements only depend on the new displacements and the old momenta depend on the new momenta, that Jacobian has a quasi-diagonal form, so it will be given as a product of two Jacobians, one associated with the change of the variables for displacements, and another for the change with the change of variables for the momentum. Now, in order to calculate these Jacobians, we need to have an explicit expression relating all displacements with the new displacements, and these are given in here. So by differentiating ui with respect to y lambda, we will get this expression. And in fact, when we take the determinant, this will be a determinant like this. Similarly, we can calculate this Jacobian for the momentum. Their relationship is here, so that derivative would be that coefficient. And again, when we take the determinant, it will be something like that. It's easy to see that the masses come in a different way, one with a minus half, another with a plus half, so they cancel out. the determinant of the eigenvectors is actually equal to 1, because the eigenvectors, when placed as columns, form a module matrix of the dynamical matrix, and we know that this is an orthogonal matrix, and therefore the determinant of the orthogonal matrix is equal to 1. So the Jacobian of that transformation is actually equal to 1. So we can easily replace the old phase space with a new phase space in the statistical integrals. Okay, now let's consider those integrals. So let's consider a statistical average of some dynamical variable g lambda, written already as corresponding to a particular normal mode lambda. So then we will have this statistical integral. We have already benefited from the fact that the Hamiltonian is additive, and therefore the statistical sum would also be written as a product of statistical sums associated with each normal mode. So this g lambda, as depending only on the particular lambda, would only modify the statistical integral for that particular lambda. All other integrals with lambda prime not equal to lambda would be actually the same as z lambda and would cancel out. Therefore, this integral can be written explicitly like this, only for the lambda normal mode, where z lambda is the statistical sum partition function for this particular degree of freedom lambda. It can easily be worked out into this expression. This is just a statistical sum, classical statistical sum for a single harmonic oscillator. Now let's apply this general result to the statistical averages of various positions and momenta in the new coordinates at the initial time. So we assume that initially the system was at equilibrium, and then it would propagate in time according to these equations. So these quantities we shall consider as statistical, corresponding to the canonical distribution. So they are sampled with respect to the canonical distribution with this Hamiltonian. So if we calculate, for instance, the average of y lambda naught, so y lambda naught would then appear here, and you see, because the Hamiltonian h lambda is quadratic with respect to y lambda, that integral over y lambda would be the integral of an odd function with respect to y lambda, because the integral is taken between minus infinity and plus infinity. So that will be equal to 0. By the same token, p lambda integral would also be equal to 0, and the integral and the statistical average over y lambda and p lambda prime with different lambda and lambda prime would factorize into averages of y lambda and p lambda prime would also be equal to 0. So the first momenta are equal to 0, and also the second off-diagonal momenta are equal to 0 as well, of y and p. So let's consider general correlations of y lambda and y lambda prime. This can also be easily calculated if lambda and lambda prime are different. That would be 0. But if they are the same, you need to work out this integral over y lambda with y g lambda replaced by y lambda squared, and this is what you will get. And similarly, the calculation can be performed for p lambda prime. So concluding, these averages can easily be calculated in the normal coordinate representation. Now we finally are able to calculate statistical averages in the original site representation. So now, for instance, if we take the correlation function like this with u, I, and uj at initial time, then these quantities are related to the normal modes, while these expressions where we take time equal to 0. And this way we arrive in here. Now, taking this average from here, we would be able to finally write our correlation in this very neat form. we can easily find that this correlation is equal to 0, and the correlation of the momenta is equal to that. So now we know the correlations at initial time. We have just calculated them. We are able to calculate correlations at time t and t prime. So let's calculate this particular quantity. In order to do this, we need to take this formula at time t and multiply it with the same right-hand side, but with the time t prime, and then take the average. And when we do take the average, there will be products of averages of u with the u, p with the p, and u with the p, with different indices. And these are given by expressions here, here, and here. So we have just worked them out. And after some rather long algebra, you would find that that particular expression is equal to 1 over beta and sum of the cosine functions over all normal modes. Next, what we shall do is to take Fourier transform of that expression. So we expect that correlation functions like these ones, while the system reaches equilibrium, would depend only on the time difference, and therefore we should be able to take the Fourier transform of both sides. So if we take the Fourier transform of the left-hand side, this would be just the Fourier transform of the velocity, momentum autocorrelation function with this prefactor of the mass here. In the right-hand side, however, if we take this Fourier transform of the right-hand side, we find that it is equal to 2 pi over beta and the sum of the delta functions. And this sum of the delta functions is actually the density of state, phonon density of state of our system. So that means that in order to calculate the vibrational frequencies of our system, one can actually run molecular dynamics simulations and calculate the Fourier transform of the momentum or velocity autocorrelation function, and the peaks in that distribution over omega would give you vibrational frequencies. And this is an example of that calculation here. So we have a box with water molecules. So this is a liquid, and it is not a crystal, and therefore it is not a harmonic system at all. However, we do see here two peaks at these particular frequencies, and this correspond to the well-known vibrational modes of the water molecule, bending and asymmetric stretching. Of course, the peaks are broadened because this is a water. There are many other contributions. In ice, they would have been much better defined, much narrower. But this is what we have in the real simulations of a real system.